The first module in the active treatment system example is the pumping module. Here's what the pumping module looks like when it is first opened in AMDTreat version 6.0. The current version of AMDTreat Pumping Module is designed to model one specific type of pump, a vertical turbine line shaft pump. These pumps have a drive motor on the surface connected by a drive shaft assembly to a turbine pump bowl assembly located downhole at the desired pumping depth. Vertical turbine pumps are the most common and most efficient type of high-capacity influent pump used at mine drainage treatment facilities, but other pump types do exist, such as submersible pumps, and they are also employed at mine drainage treatment facilities. But again, the current version of AMDTreat software only considers vertical turbine line shaft pumps. The format for all AMDTreat modules is that input variables are located along the left side of the module, and the output variables are displayed on the right side of the module. The first section, vertical turbine pump borehole, in the upper left-hand side of the module, allows the user to select the number of wells and the borehole sizing and to define the cost associated with the process of borehole construction. The user should note that vertical turbine pump borehole portion of the module only provides cost calculations based upon selected values for number of wells, selected diameter, and drilling depth. Pump sizing is determined by selections made in the conveyance pipeline section below. Consequently, once the horsepower rating has been calculated, the user should then consult with pump manufacturers or equivalent pump system experts to verify that appropriately sized borehole has been selected and matched to the appropriate size pump. For the example, the following values will be selected to model vertical turbine pump borehole. One borehole will be modeled in this example with a total drilling depth of 150 feet. Note that in this version of the software, drilling depth is described as the depth to the mine pool. However, this should in fact represent the total depth of the borehole, which in all cases will be deeper than just the mine pool elevation. This is necessary to accommodate both the physical placement of the pump to allow for sufficient placement below water level to avoid cavitation, and also for adequate drawdown needed to control the mine pool. Consequently, this depth should represent the total required drilling depth. Subsequent versions of the software will be revised to indicate total drilling depth. The borehole sizing multiplier increases the outside diameter of the borehole to account for casing and grouting of the borehole. In the example, a 16-inch diameter borehole is selected, and applying a 1.5 multiplier would result in a 24-inch diameter borehole. For larger inside diameter boreholes, a less than 1.5 multiplier is likely more appropriate. Again, the user is encouraged to contact drilling contractors for specific recommendations for outside diameter in order to select the appropriate multiplier. The next section, progressing down on the left-hand side of the pumping module, is conveyance pipeline. This section contains the options for pipeline, appurtenances, and installation, as well as the static head, percentage of incidental head losses, and desired flow rate. Total static head, flow rate, pipeline diameter, and incidental head losses are also used by the AMDTreat program to calculate the required vertical turbine pump horsepower. In the example site, the following changes to default values in the module will be made. Flow rate 300 gallons per minute, total static head 70 feet. This is the head difference between the lowest desired mine pool elevation and the invert elevation of the treatment system. Pipeline length will be 400 feet, and all other input variables will remain as default values in this example. Note that if the user is planning the use of multiple pumps, the flow rate entered by the user should be divided by the number of pumps that are planned to be used. The current version of the AMDTreat program does not automatically do this based on the number of wells selected in the vertical turbine pump borehole section of the module. If multiple pumps are planned, especially if they will be using separate conveyance pipeline, it may be a better approach to model the site by evaluating each pump system in a separate AMDTreat pumping module. A drop-down menu with the SDR value is provided in this section. SDR, standard dimension ratio, is a method of rating the durability of a pipe against pressure, and it describes the correlation between pipe diameter and pipe wall thickness. Pipes with a lower SDR diameter can withstand higher pressures than the same diameter pipe having a higher SDR number. The program guides the user in selecting the appropriate SDR rating for the pipe diameter selected and the operational conditions. The program will issue an error message if the SDR value selected by the user has an insufficient pressure rating. The program will also notify the user in the case where an SDR value selected results in a pipe selection having a pressure rating that significantly exceeds the expected operational pressures, and where one or more higher SDR number pipes could be used to lower the estimated cost. Total static head is the difference in elevation between the liquid levels of the intake, or in most cases the lowest achievable elevation of pumping, as pumps in general require a minimum water level be maintained above the pump intake and discharge of the pumping system. In this example, the total static head is 70 feet, and it represents the elevation difference between the lowest anticipated mine pool elevation and the invert elevation of the reaction tank. The next section of the pumping module is vertical turbine pumps. Within this section, the user can specify the number of pumps, pump efficiency rating, a pump sizing factor, unit cost for electricity to operate the pump, and concrete unit cost to account for capital costs associated with pump motor foundation pad construction. The user can also specify operational time, maintenance factors for pump and pipeline annual cost considerations. Finally, the user can choose to include a variable frequency drive soft start system for the pump. In the example site, no changes to default values in the module will be necessary. The soft start VFD option can be installed on the motor of the pump. The VFD allows the user to control or adjust flow rate of the pump. The soft start component is also beneficial where there is an emergency backup generator system needed, as it can reduce the size of the generator needed due to the high starting torque on the vertical turbine pump. If the user keeps the box checked, the cost of a soft start VFD system is included in the capital cost for the pumping system. Additionally, VFDs can significantly reduce operational costs as they can allow for a much more precise mine pool operational control. For example, during low flow seasonal conditions, pumping rates can often be reduced, thus reducing electrical costs, treatment chemical utilization, sludge generation, and overpumping, excessive lowering of the mine pool. In many instances, mine pools that are held within a narrow range of operating levels show significant improvement in water quality over time, as compared to similar pools where flooded elevations are allowed to fluctuate significantly. Lastly, the decision to include a soft start VFD system may depend upon the utility company providing electrical services. In many cases, for new applications for electrical load, utility companies may or will require VFDs on all motors above a given horsepower rating. Contacting the utility provider in advance of the project design is recommended. To reiterate, one final note for this section of the pumping module is that while the user can select a number of vertical turbine pumps for the project, the AMDTreat Pumping Module does not divide the user-selected flow rate entered in the conveyance pipeline section by the number of pumps the user selects in this section. Consequently, in certain modeling and costing scenarios, the user may opt to model the site by evaluating each pump system in a separate AMD treatment module. The help file and tooltips for the main user interface, as well as the Getting Started tutorial, contains the additional information for opening and working with multiple modules. Upon finishing the vertical turbine pump section, we have completed all of the input information needed to generate the output summarized on the right side of the pumping module. The sizing summary at the top right reports the pipeline and pump characteristics. The next section is capital costs, which summarizes the major equipment and material item costs to construct the pumping and influent pipeline system. Our example site indicates the pumping capital cost of $47,249. Next is the annual cost section, which reports annual electrical cost and pump and pipeline annual maintenance costs. The maintenance cost values are based on percentages chosen in the vertical turbine pump input section of the module. The estimated annual cost for our example site is $6,330. The last section on the right-hand side of the module is the net present value section. The net present value has multiple variables used as part of the calculation and represents the amount of present-day funds that would be required to be invested at the assumed rate of return and inflation rate. That, in turn, would generate sufficient revenue to cover the cost of the operation and recapitalization items in the module. The first three items shown are terms of analysis, inflation rate, and rate of return. To change any of these three variables, the user must adjust them at the main user interface by selecting net present value at the top of the screen. These variables apply to all modules selected for a project. Recall that in the introduction section of this tutorial, the menu option on the main user interface where these changes can be made was displayed. For our example site, a 75-year term of analysis, inflation rate of 3.1%, and an effective rate of return of 8.45% was selected. The list of pumping module items to be recapitalized and included in the net present value analysis is the last item in this section. There are 6 items included by default to calculate the net present value for the pumping module, including default values for life cycle and replacement percentage for each item. The capital cost for each item is automatically used, so that if the cost for any of the items listed is $0, it will not be included in the net present value calculation. The user can uncheck the box next to each item if they do not wish to include that particular item for the net present value calculation. For our example site, all of the default items are included. However, the default life cycle frequency of 10 years for the pump, soft start, VFD, and control panel were all changed to 20 years. The resulting total net present value for the pumping component is $133,199. This is the initial investment required to provide the funding needed to build and sustain the pumping and influent pipeline portions of the treatment system for a 75-year period, including all operation and maintenance and replacement costs for the materials. That concludes the pumping module portion of the tutorial. Next, we will discuss and examine the lime slurry module in the active treatment tutorial entitled Module 2 Lime Slurry. Thank you, and once again, please refer to the module tooltips and the online help files for additional information.